Hello everyone, and welcome to the Zurich Instrument Sensor Characterization and Control webinar. My name is Meng Li. I'm a application scientist working in the marketing and sales team at Zurich Instruments. I am very glad to be your host today for this webinar. And before we start, I hope that all of you are healthy and safe. And I would like to assure you that we set up this webinar by adhering to strict rules of prevention and social distancing as required in the light of the COVID-19 pandemic. This webinar is organized in the following order. We will begin with a brief introduction to the topic, followed by one section focusing on sensor characterization and another one on sensor control. In both sections, the presenter will guide you through by running a live demonstration. I would also like to add some important and practical information. To deliver the webinar in the best quality, we have disabled the chat function and also muted all the attendees, such that everyone can concentrate on the presentation. If you have a question to our speaker, please feel free to send it through the Ask Question tab at the bottom of your Zoom window at any time. I will collect the questions and we will look at them at the end of each section. If there isn't enough time to answer all of them, don't worry, we will provide you with a summary of the answers sent to you in a following up email in the next 10 workdays. Okay, so let's now welcome the presenter, Dr. Kivanç Esat, my colleague at Zurich Instruments. He is also an application scientist and our sensor and MEMS expert. In addition to these skills, Kivanç also got practical experience in photonics and SPM during his previous research. I'm sure that we can all expect a good story from him today. So Kivanç, I will hand it over to you. Please go ahead.
Thanks, Meng, for the kind introduction. So let's dive into it. As Meng said, today we will talk about sensor characterization and control using Zurich Instruments lock-in amplifiers. These sensors could include, but not limited to, inertial devices such as MEMS gyros, accelerometers, cantilevers for atomic force microscopy, light detector, impedance-based devices such as humidity sensors, and so on. Even though the working principles are very different, the way we interact with such devices are rather similar. It requires some input signal to the device under test, DUT, and then we measure its response. But of course, it's always more complicated than that, and often it is required to apply complex control schemes. Hence, an accurate characterization of the device properties is essential. For this both characterization and control purposes, one common approach is to develop an application-specific circuit, ASICs, which is cumbersome and time-consuming during an iterative development process. To tackle this challenge, Zurich Instruments has combined time and frequency domain analysis tools with feedback loops, lock-in amplifiers, arbitrary waveform generators, and impedance analyzers in a single platform. And today we will look into these digital tools. This is our agenda for the day. I will start by sharing a few words about Zurich Instruments. And then we will dive into sensor characterization, but I will start with a brief overview of how lock-in measurements work. Then as the next step, we will look into sensor control, when we do close feedback control loops. All right, so at Zurich Instruments, we aim to provide dynamic signal instruments with state-of-art performance, but with still plug-and-play user experience, where your computer becomes the cockpit for your measurements. This is also how I can deliver this demonstration with the instruments I have on my desk today. Starting from commercial off-the-shelf components, we build high-performance equipment, and our software offers efficient implementation with many functionalities and also easy-to-use interface with application programming libraries. And combining this hardware and software aspects, we started by providing lock-in amplifiers and expanded our portfolio starting from this experience. Now, let's have a look what we have to offer. As promised, since we are now looking at the characterization, we need to know how we actually do the measurements. So which is lock-in measurement. So we will look into this now. And to motivate ourselves, we can look at this cartoon, which shows typical noise environment, where this is the amplitude and the frequency here. Here we have the white noise that sets the baseline for higher frequencies. Several spikes appear from various sources. 1/f noise picks up at lower frequencies. And now, if you want to measure around at DC or at low frequencies, the signal that you want to capture will be embedded in noise. To be able to measure such signal, one way to do it is to modulate this to a higher frequency where the noise is lower. So this is essentially what we do. We modulate a signal at noisy environment. To do that, we basically modulate with a sine generator or a wave generator that goes through the DUT, and also the reference signal goes to the lock-in. And the lock-in then provides us the amplitude and phase of this signal. How does it work with our lock-in amplifiers? This signal first is digitized using an analog digital to conversion. And after this, everything happens in the digital domain. And this is the key aspect of our lock-in amplifiers. So the signal is then first mixed with an oscillator. And by the way, you can use this oscillator to also drive the DUT using the output channels of our instruments. And then the mixing happens at dual phase. And then the mixed signals then filtered with a low-pass filter in order to capture only the important part of the data or the mixed signal. This provides us with the Cartesian components of this demodulation process, and then we can capture the amplitude and phase. So just to recap, this demodulation process starts with analog to digital conversion, mixing with a reference signal at a given frequency, low-pass filtering that is determined by the bandwidth and order. I will not go too much into detail, but these two are very important parameters for this process. And now, since we have the information required in the digital domain, we can do further analysis, which can be parametric sweeping or building up control loops. So now we know what we are dealing with, and now we can look at various tools. So we provide different lock-ins. I also have them on my desk here. They are, most of the tools that I will be talking today can be performed or used with all these three instruments. Main differences are the bandwidths, the frequency range that they can work with. For instance, MFLI can work up to 5 megahertz and UHFLI 600 megahertz. And also input channels vary. But also each of them comes with unique properties. For instance, MFLI can be configured as an impedance analyzer. HF2LI can measure two current inputs at the same time. And UHFLI can be configured as an arbitrary waveform generator. And on top, all the instruments are controlled by the Lab 1 user interface that provides many tools. And I will show you these tools today during a live demonstration. Now we can jump into demo, but I will now look at the frequency and time domain tools only. And I will do it with UHFLI lock-in amplifier. And the reason I choose UHFLI is because I want to also show you chirp FFT among these tools. Hence, I need an arbitrary waveform generator. And UHFLI, as I mentioned, comes with it. And what is an arbitrary waveform generator? It's essentially an instrument that can generate a user-defined waveforms as complex as such. And also it provides triggers, markers, etc. And during this live demo, first live demo, we will look into Lab 1 basics. We will look into frequency response of the instrument, step response, and then chirp FFT. Now I need to switch my screen to the user interface that we will be looking at. So I'm actually sharing you with my Chrome screen. And then since I have three instruments on my desk, you see the three instruments. And now I will activate UHFLI lock-in amplifier. And the instrument starts. Several tabs will appear in a few seconds. And now there we have. I will first want to focus on the lock-in tab. So what we have in the lock-in tab here is we see several signal inputs. So you have two actually, so two of them are listed, where you can also change the input ranges, the coupling settings, etc. that is very convenient for convenient analog interfacing. And then we have signal outputs listed at this part here. We have 2 again, and similarly you can interact with them. We have several oscillators and demodulators. So depending on the instrument you have and how they are configured, the number of oscillators and demodulators can vary. And in this case, we have 8 for each. What I'm going to do now is I will take this BNC cable and connect it between the signal input 2 and output 2. Just basically loop it back. And then I will activate the drive. And then with the scope, you can already see the signal, which is the orange curve, that is the channel 2. Now, but you can see that it's a little bit noisy because I'm driving 100 millivolt peak voltage, and I am measuring it 1.5 range at the moment. But so that I am not using the ADC to its full extent. To achieve this, I can click this auto button and it will readjust the range, and then we will see much better signal to noise. I can also now introduce my device. So today I will be using this quartz oscillator as my sensor. I have 2 here, I will only use 1. And then I will also connect it between these remaining channels. And I start driving it. And already see the signal on the scope as well. It is much less amplitude, and also we have a phase delay that comes from the DUT. Now we can start using the demodulator itself. So we are using this oscillator at the moment to both reference this orange curve and the blue that goes through the oscillator. It's 1.8 megahertz. And then the demodulator is configured here. So we have low pass filter, and I can click this button to start the data transfer for the demodulated data. Just for maybe it would be a bit more intuitive for you to see. You can also look at in this chart for each to each demodulator. We have the signal input here again, signal output configured here. We have the reference oscillator, again, the same frequency that I was showing before, and the low pass filter then provides us the information. And you can configure its order and bandwidth. Now to get the demodulated data, I will grab this numeric tab, which already shows me around 30 millivolt amplitude and this value of phase delay that is coming from this device. But now, of course, we have the information in the digital domain. So we can actually do more than just looking at numbers. For instance, we can grab this plotter tool and look at the time trace. Now I need to actually make a reminder here. I am using this, I'm looking at my screen that is 60 frames per second. So I actually see very fast numbers changing, and the graphic is updated very fast. But since we are broadcasting over the internet, there is bandwidth limitations. And if you see this a bit laggy, please have a look at the recordings afterwards. They will look much better. So this is the plotter tool now. I'm looking at the real-time data. Now we can also activate to plot the phase, for example, in the same figure. Now just to, not to get confused, I'm overlapping 2 measurements on top of each other, which has different units. So basically how it works is if you activate phase here, you see the phase in this y-axis. If you activate R here, you will see the amplitude. All right. But now we can actually start characterizing our device. That will be this oscillator that I was showing you. For that, I will grab the sweeper tool and configure it as a frequency response analyzer, but it can also actually sweep many other parameters that comes with the instrument, such as bias voltage, etc. And then I will sweep from 1.8 megahertz to 1.9 megahertz. So it is already sweeping. Now we see the resonance already. To be able to see the resonance with high resolution, I will zoom in and then sweep again. So it's already getting better, and perhaps a little bit more. So it's also nice because we have a quite responsive user interface. And also you can look all the measurements in a row, or now for the moment, I will only look the last measurement. so that we don't get confused. And we can activate the dual plot, so we also at the same time look at the phase. And to look at or analyze this data, we can use these markers to, for instance, have a look around where the resonance is, or use second marker to have an idea about the bandwidth, or better, we can use the provided math tools to do a resonance fit to get the, so you can see the dashed line here, which already done, and then it provides us the quality factor, the bandwidth, center frequency, etc. Now I will actually drive it at the center frequency. So now look at the level of the ADC. So this actually shows that we have 400 millivolt input range, and we are only occupying just, I don't know, 10% of it or so. If I start driving this at the resonance, you will see that we actually have much higher amplitude because it is now amplified. Okay, so this is how you can use the instrument as a body analyzer. And what I want to do is to look at, as I mentioned, the step response of this instrument. What I will do now is, since I'm now driving at the resonance, I will just stop the drive and see how the resonator relaxes over time. Of course, I can use the plotter and look at the time trace, but to make things a bit more convenient and maybe easy to post-process afterwards, we will do a triggered data measurement, data acquisition. This is done by this data acquisition tool we provide. And for this, I need to only set a trigger, which is, for instance, let's say 195 millivolts. The reason I choose this value is because the R, the amplitude that I am currently measuring, is around 200 millivolts. Basically, you can see the value here. I will also adjust the filter settings so that we capture it right. Now I arm this measurement. So the moment I will switch the driving, we should see the step response. I also need to, of course, do it for the negative edge because I am closing the drive. All right. So this is what I'm talking about. At this moment, we were driving the oscillator, so it was around a bit above 200 millivolts. And at this point that I'm showing now, we stopped the drive and the oscillator relaxed. And you can see it, since we have a high quality resonator, oscillator, we have a relatively slow decay that spans over a few milliseconds. All right. Now, we were looking at this frequency response, but if you want to actually look at the frequency response over a broad frequency range, the sweeper might take long time because now we need to sweep each data point one at a time. To tackle with this, we can do chip FFT. And for this, I will actually recall one of my previous settings to run the run the VHF-LI like an amplifier as an arbitrary waveform generator, which will then provide us with the chirp signal. It's very convenient, so you can save various settings. Now I will actually load this chirp FFT settings I made before. You click load, and then the interface will restart and then load the old tabs that I was using before. Now we can already see that the AWG is open and the scope, and the lock-in is configured in a similar fashion. How the AWG works is essentially you write down an instruction sequence as I show here, and in the end one of the instruction is driving a chirp signal with a given starting frequency and stopping frequency with a given number of sample points. And in this case, we will be driving it around 1 to 5 megahertz. And I activate the AWG, and you can see that the outputs already for both channels are controlled by the AWG. And if I go to scope now and start running, I'm now zooming in between 1 to 5 megahertz, maybe also in the y-axis. So the orange curve you see here is actually what is going through this MTBNC cable, which we then provide many frequencies. Just for the, to be clear, the scope now is running in FFT mode. So we are actually looking at the frequency axis here, not the time that I was showing before. Okay, so the orange curve is now the actual frequency band that we are driving our device, the oscillator with, and you can already see a few resonances appear. For instance, we were looking around 1.8 megahertz, which was this peak here, and now we can also characterize very fast and the others as well. So this is the chirp FFT. Now we need to switch gears. So I will change back to my slides. So what we did was the frequency and time domain tools. Now we will look into the impedance analysis. And as I mentioned before, the MFLI can be configured as an impedance analyzer. We also provide another unit or instrument that is called MFIA, that is the impedance analyzer itself, but technically these are the same instruments, so they can both do the job. And this instrument or the impedance analyzer comes with this text fixture where you can conveniently place in the front panel of the instrument, and you have pins here to introduce a PCB mounted device. And in this case, I will be using a photodiode. I place it here and put it in. For the next part, so this next part of the second part of the demo, I will be looking at the impedance analyzer basics from our Lab 1 interface, and then we will do a transient capacitance measurement on this photodiode that I just placed on the instrument. Okay, so let me go back to my user interface again. I will start a new instance. Again, we will see the list of the instruments here. Now I need to connect the MFIA. Hi, everybody. Sorry for cutting in like this, but as you might recall, we had a small communication problem with the MFIA impedance analyzer. And this was because of this cable, and the device was not streaming data as it should be because of the wrong cable that has been used. And I just changed the cable so we can try it again. Here you see on my shared screen the same interface where the same MFIA is located. I will basically start the communication with the instrument. And now you see that a bit different interface than what I was showing you with UHF-LI lock-in amplifier. Instead of the lock-in tab opening, we see an impedance analyzer tab, because the MFIA is configured as an impedance analyzer at this point. What is different is we have the measurement control section here, which allows you to set up how we drive the device and how the interface happens, how the advanced settings of the measurement, etc., can be set up here. Also the oscillator frequency as well as the test signal voltage. In this tab here, we have the equivalent circuit described. We can select 2 or 4 terminal measurements. You can also select the representations for your DUT, for the device that you have. And if you change the representation, you will see directly this figure here changes with the chosen settings here, or like, let's say, 2 terminal with this setting. But now for the measurement we have for the diode we are using, I will go back to the 4 terminal measurement and then the parallel capacitance, parallel resistance. Here in the measurement settings, you see the real and imaginary part of the impedance, and as well as its absolute value and the phase of this measurement, and the frequency as well. And if we change the frequency here from 1 megahertz to 2, you will already see it's changing. And as well as the represented parameters, that will be the parallel capacitance and parallel resistance. And here we have around 24.6 picofarad parallel capacitance. Now, of course, watching these numbers are not that easy if you want to see what is happening. That's why I grab in the plotter tool that we were showing before as well. And now I will try to block the light that this photodiode sees, and you can see its response is changing. And this is basically a photodiode, a photosensitive sensor. What I'm going to do now, instead of just driving with a with a periodic signal, I will also apply a bias voltage, and I will vary this bias voltage to do capacitance transient measurement. For this, I will grab another setting file that I prepared before. That will be the sensor diode DLTS, and we are loading the settings file as we did for the UHF-LI. Again, we have the impedance analyzer configured, but as I mentioned, we are now applying a bias voltage as well on top of the test signal that is a periodic signal. And this bias voltage is like this. We have the scope, we can see it in the scope basically, and what we have is we apply from 0 to minus 21 millivolt bias voltage with as a square wave with 1 millisecond duty cycle. And what I'm going to do is look at this short time window where we only see the negative edge of this square pass within a very short, like roughly millisecond time window, so that within this change from 0 to minus 21 millivolt, how we can observe how the capacitance changes. So this is essentially a step response which we were looking at with the data acquisition before, so that we have the data acquisition tab, which is already configured. So I will run the measurement. This blue curve you see here is the bias voltage that we are applying from 0 to minus 21 millivolt roughly. And the orange curve here is the representative parameter, that's the capacitance. Let's have a look with the cursors. So now we have a roughly 100 femtofarad, 140, 30 femtofarad step change. And this happens over the course of only few microseconds. And we can also, of course, vary the bias voltage, the amplitude of this bias voltage. So I will do now around 10, and then the capacitance step will also decrease. Now it became around 73 femtofarad, and then we can even do further decrement to -5 bias amplitude, and then you can even reduce to only a few femtofarads. And this measurement essentially shows us that the MFIA can be used for fast and precise capacitance transient measurement as well. With this, I will also conclude this part of the demo, and then we can go back to the slides that I was showing the live show and recap this section. Okay, I will quickly go back to my slides and recap. So what we were looking at the Lab 1 user interface, and we looked at this Lakin measurements, how it is done. We look at our resonator as a sensor and look to its response using check the amplitude and frequency response. We do actually use the sweeper to get the frequency response around the resonance to get its quality factor, bandwidth, amplitude, etc. We looked at the step response. Then we did chirp FFT to do a very broad frequency range, frequency response of the instrument very fast. And then we look at the capacitance measurement, how we configure the impedance analyzer. And with this, I will end the sensor characterization part, and we might have few questions to answer at this point. So I will give the mic back to Meng. I'm not sure if I can hear you, Meng. It seems we have a technical difficulty for Meng to tell me the questions, or at least I don't hear it. But at least I actually see a few of the questions, so I can have a look. Maybe The first one, it says, is it possible to get the 2F signal from a typical Lakin amplifier? Yes, we can do. We actually configured this as like we have the Lakin amplifier tab, which I was showing you. And you can also get the several other harmonics as well, where you can set up your Lakin tab. So it is possible. From TS, I have a question actually. Can you please explain how the data transfer rate related to the data shown in the plotter or sweeper is the maximum sample rate for those tools, are how should I interpret the transfer rate? This is a good question. Yes, this is actually what I was also tackling with. So the transfer rate, you can set it up as you prefer. So I will go back to my interface. So this is the transfer rate you can set up. That is essentially how fast you can send the data to the computer. And of course, faster it is, more data you send in a given time. But also, for instance, if you do a sweep measurements, if you do faster it is, then of course you then have to do a fast sweep as well. So sweeper, that is how it's related. It will accelerate the sweeping to one extent. And for the plotting to plotter, if you do use if you increase the data transfer for plotter tool, then you will have more data points at a given time. So that would be the case.
Okay, so Kivanç,
Meng, you come in.
Could I step in and ask this next question? I think
Yes.
there is a bit audio connection issue, but now really everything should be back and clear now.
That's okay. So we actually already looked at 2 of the questions. Maybe we can have time 1 or 2 more.
Yeah, you did it pretty well. And let me ask the next question from the audience.
That's great.
I think, let's put it this way. So in your Lab 1 demonstration, you showed really a very nice user interface. If I want to use an API, let's say Python or LabVIEW to control it, is it possible, and how easy to use it?
Yes, definitely possible. So we provide Python, MATLAB, LabVIEW, .NET, C APIs, and they all come with several examples. Then you also, even the modules that I was showing you, you have an example, for instance, the scope, and you can just load it and start running it, and it will work right away. So it is quite straightforward and is used a lot by our existing customers to incorporate the instruments with another existing setup. So it is quite convenient.
Okay, that clearly answers questions. And I would also like to add that on the instrument, we actually have a nice command log. If you click it, then you will be able to see all the steps that we have performed today. And for beginners of the API user, they can simply copy and paste the same command to your compiler and run it. Yeah, it would be very easy.
True. Let me show you actually. So this command table that I am loading now is now actually in I think it's in .NET or so, and you can directly see all the settings I was doing over this moment. And you can directly copy paste this information to your command. You can also configure it as Python, etc. In this case, I was doing Telnet, and I will now switch to Python, for example. Let me do something. Let me activate this friend here, and then go to command table again. And as the last item, we should see now here a Python command to activate the button that I was just pressing on the user interface. So this is very easy to do.
Okay, indeed. And it looks like we have to move on. And dear audience, we apologize for the tiny issue just happened, but please feel welcome to keep asking questions. We got another question and session in the end of the webinar. And Kivanç, I will hand it back to you. Please resume your talk.
Thanks, Meng. So I will switch back to my slides. All right, so we can now continue with the sensor control part of this webinar. So far what we did was an open loop measurement essentially. So we were driving the DUT or our device under test with a sine wave or periodic wave, and the Lakin amplifier was providing us the amplitude, phase, etc. But there are certain issues here. So one is small perturbations, like for instance, if I touch this resonator, etc., would change device's behavior. And the perturbed device state can settle to another arbitrary state. And also, as I was showing with this step, response measurement, the device has a slow response. And for faster device response and to achieve required behavior from the device, we need to use control loops. So this is the key. How do we do this? We essentially, again, do the measurement, and then the measured information will then go to a loop filter, and then using this result from the loop tape filter, we will drive the device so that our information remains as we want. How does this work? It starts with measuring again, and in this case, again, this is a sort of an open loop behavior, right? We have the demodulator that measures the phase at a constant frequency, and the frequency is now controlled by an oscillator, numerically controlled oscillator. Now we add the next part, that would be the loop filter. What is this? Then we set a set point for the phase we want the device to be at. And then the resulting signal will be an error in between the set and the measurement. And then the PID will then update the drive signal so that the numerically controlled oscillator will drive the instrument with a different frequency. So to recap, we do the measurement, we decide on a set point, then the error signal is generated. We apply the PID, and this PID will then change how we drive the instrument. What I described you so far in this example is actually a phase locked loop where we lock the phase to a set point to be able to track the frequency of the device under test. Of course, we can do it more generalized. Instead of phase, we can use an amplitude, for instance, or any other signal that we have as an input. And then the PID controller will try to set it close to the set point using by varying the outputs that we use to drive the instrument, or drive the device. So basically the important thing is, how do we configure this PID parameters? And the answer to this is, of course, we need to know the device response in the closed loop system. This is given by the transfer function. And once we know this, it's possible to model a closed loop behavior of the system. But this might sound a complex scheme. However, Lab1 offers a PID advisor where you can select most common device models. We also provide what these models actually are, and there's no secret basically, and then all still remain under your control. And since we have a resonator as the device under test, we need as a model the resonator frequency and resonator amplitude, where the frequency and the quality factor are the important parameters which we actually already calibrated. For the sensor control part, what we'll then do is, as I described, we will close a phase lock loop, PLL, and then on top, we will close another PID controller to set the resonator's amplitude to a constant level. So this is also referred to as automatic gain control. So we will do this automatic gain control scheme. Again, we can do this operation with all these three instruments. And then, of course, again, there are some unique properties as well. And the most important part would be the maximum provided loop filter bandwidth with these instruments. I will again continue with UHFLI since we already have it set up. And this last part of the demo, we will look at the Lab1 PID PLL type basics. We will close a phase lock loop. we will close another PID to get automatic gain control. For this, again, I need to share my screen again with my user interface. Let me close these tabs. And now I am looking UHFLI. I will again reconfigure it or like call my old setting files to save time. Good. And let me run the sweeper once more, so we actually know what we are dealing with again. So this is our resonator. Oh, I ran it twice. That's fine. And again, we have the quality factor and center frequency as well. So I will continue driving the resonator at the center frequency, of course, megahertz. Right. So far we just did what we did before. Now I will go to this PID PLL tab. What we have here is the configuration of the PID PLL itself. So here we have the input. Since first we will configure a PLL, phase lock loop, we need to measure the phase of the device. And the set point would be the, since I want to drive it at the resonance, I want to track the resonance, I want to set the phase as a set point, the phase we measure from this fit. So it is around minus 90.61 degrees, right? And then as an output, we will change the frequency. This should be around the center frequency that we measure. Now, in principle, I can now start playing with this PID and try to make it work. But of course, it is easier to use the advisor. What we will do is use the DUT middle as the resonator frequency. And then again, I need to configure the resonance frequency here. And then we need to set the quality factor, which is around 19 kilo. Perfect. And now the last parameter, I need to choose the target bandwidth. This bandwidth is basically the closed loop bandwidth that tells how fast this feedback loop will cope with any perturbation. So, and I will choose now it to be around 1 kilo. This is the targeted one. And then the advisor will advise me somewhat around this value. So we have the calculated bandwidth around 1.3 kilohertz. And you can already see it is calculated transfer function. And then with this button, I will load these parameters to the PLL tab, which will actually drive the instrument. And I will click this button. And this green dot here shows me that we're already in lock. And this is our error signal. Let me show you how it looks like. So I will now grab the frequency of this measurement. And you can see that over the span of like basically around 1.8 megahertz, we have a standard deviation that is around 20 millihertz. So this is basically where we have our resonator. The oscillator has the resonance frequency at around, and it is moving around, of course. So we are trying to track it. But now let me also grab the amplitude of this measurement. You can see that it is fluctuating quite a bit. And actually, if I tap the resonator, now it feels that, of course, but frequency recovers, but the amplitude doesn't recover that fast. And it can even go to another different arbitrary state because I'm not driving this resonator. I'm not controlling its amplitude. Look, now it is actually drifting. What I'm doing is now, to one extent, is using this oscillator as a proximity sensor, actually. But now to make things a bit better, we need to also close the loop for this amplitude. So this is the amplitude gain control that I was mentioning before. So for this, I will grab the second PLL. And in this case, now we have an amplitude around 204 millivolts. So let's aim that as a set point, and we will be looking at this value directly. So it is 204.7 millivolt as my set point. We are already driving around 100 millivolt center amplitude, and this will be our output value. So we will vary the amplitude that we drive this device with. And in this case, our DU2 model should be resonance amplitude. And again, we need to write down the correct resonance frequency and Q factors. So that's why I go back to the sweeper. And this is the Q, around 19.27 K, and then the center frequency. Maybe I can also make a remark here that all the tools we have that I'm just opening various tabs, they can all work simultaneously at the same time. So you can actually do this complicated stuff. You don't need to configure for sweeping and then load it again to be able to achieve the data. This is quite convenient. Okay, so the last step for the advisor, I need to choose a target bandwidth, and this is important here. The target bandwidth for the second controller for the amplitude should be slower than the PLL, phase lock loop. So now in this case, I have 500 Hertz. Let's advise again. And then we see transfer function. And now we have the new PNI values. We can load them back and then close the loop. All right. Now, if I go back to plotter, now we can see R is also quite flat at the moment. And the standard deviation is around, for 200 millivolts, we have 16 microvolt. And now if I tap it again, it will also recover and will be always at this amplitude. So now we have a perfect oscillator. Okay, so this is what I wanted to show you in the control part. Let me go to my slides again and let's recap. So what we did was we closed the phase lock loop to be able to track the frequency of the oscillator, and then we close an PID for the amplitude control. So basically this together it's called automatic gain control principle. So the take-home messages so far is you can use a single instrument for sensor characterization, and you can, with the same instrument again, close feedback loops and control the devices as well. And hence, you don't need to build up various circuits to be able to interact with your device that you are developing at the moment. You can run all these tools simultaneously to get together so that you don't need to reconfigure the instrument to be able to do another measurement. Since we have very convenient to use analog to digital converter layers, and that allows you to do seamlessly analog interfacing so that you have the best signal to noise ratio all this time. So with that, I would like to end my presentation. So hope that Meng now we can hear you, and then we can go through the questionnaire.
Sure. Sure.
Great.
And many thanks for giving this insightful tutorial, Kivanç. And I think we can now begin the question and answer section 2. So the first question actually is coming from the previous section. So one attendee asked, you mentioned your local amplifier can measure from DC. How is that possible? How good is the DC measurement?
I see. So what you can do is, so these instruments indeed can work from DC to its bandwidth, like 5 megahertz. So basically you can measure by setting the oscillator at 0 frequency, and it's still possible. I hope this answered the question. Meng, you think?
Yes, that's actually a very good answer. Yeah, I believe so. And on top of that, actually, if you have the multi-frequency or multi-demodulator option, you can also do, for example, AC and DC measurement together simultaneously. This will be very easy to have. That
is correct. So we didn't cover all the tools we have. Of course, I actually show a few extra of them. This mode option that Meng was mentioning. So if you want to do sideband modulation or so, you can do that with this tool, which is quite useful. Yeah.
Okay. Second question actually is a bit easy. So a user asked, so I saw actually you are working with the PID and PIL with your UHF. Is it possible to use my MFLI or HF2LI to do a similar task?
Yes, indeed possible. So let me go back to this slide I was showing before here. So all the instrument has PLL and PID options. So we call PLL because it is used for a specific case, for frequency tracking, which is used a lot. For instance, if you do, if you need to, so if you don't want to drive the drive the experiment with the oscillator inside the lock-ins we have, but another clock source, you can still bring it to the instrument and use it as a reference. For this, you need to be able to lock to it. And this is done by PLLs. So that's why we have separate PLLs. Like we call it as separate, but it's essentially a PID controller in the end. So MFLI comes with 4 PLL or PID that can be configured as I showed you. And similar to UHFLI. And then the loop, maximum loop filter bandwidth, which means again, how fast these feedback loops can cope with changes, can be up to 50 kilohertz in this case. And for UHFLI, since it has a faster bandwidth also, it can go up to 300 kilohertz. So this is the maximum we can offer at this point. HF2LI is a bit different. It comes as 2 separate options, 2 PLL and 4 PIDs, and their maximum filter bandwidth vary a little bit. So this is basically a difference between different devices, but for most of the tasks, for example, for this roughly 1.8 megahertz oscillator, all would do the job.
Okay, that clearly answers the question, I believe. And a related question to it is, well, attendee asked, how is the bandwidth in your PID and PIL relates to the feedback speed or rate?
Of course, and then I can grab this slide here. So again, we do the measurement with the lock-in, right? So lock-in measurement, so we demodulate the incidence incoming signal. And we want to, so the filter bandwidth we are talking about is the response of this whole system that I'm showing you. But we also have a low pass filter in the measurement process as well. And this low pass essentially has a time constant. So how narrow you have the band, how it will, like narrower you have this band pass, the slower the measurement will be. But of course, this is always a balance. If you make it narrower and narrower, you have less and less and less noise on your measurement, but then it gets slower. So you need to balance in between. So this is the relation.
Okay, I think this is a very good answer. And a more specific question about Meng's control. And you are our Meng's expert. I believe you can give a great answer to that. A user asked actually, for example, is it possible to feed, let's say, the output of PLL or PID1 into the input of the second PID and using, for example, auxiliary voltage to control the resonance frequency somehow?
You can do these things, yes. So we also have in the instruments auxiliary output channels. What you can do is you can route the PID output to these auxiliary channels. And then you can use these auxiliary channels again to do the lock-in measurement as well. Let me quickly show you how you can do it. I will go back to my screen. So let me grab a PID that's not running. So basically you can choose different number of inputs. This can be auxiliary input or output. And then what you can do is let's grab the demodulated data, the data that comes from demodulator 2. That's actually our amplitude at this point. And I can bring that amplitude from the second demodulator to the auxiliary output. And now, if I configure the PID to like auxiliary output 1, this will be the input signal. And then the output, similarly, you can select the outputs, oscillator frequency, demode phase, or any the other auxiliary output offsets, etc. So it is possible to do these configurations.
Yeah, that's a very nice answer. I think we can ask the next question. So
Yes.
the next question is also somehow related to this kind of integration. Is if I want to really send out an analog signal, I mean either the PID parameters or the measured demodulated data, is it possible to really send that to another instrument I have?
Yes. So you mean analog way?
Yes.
Yes, of course. Again, you can use this signal auxiliary output. For example, let's choose the auxiliary output 2 for the UHF. This is basically this channel here I'm showing, if you can see there. Then we can choose to send the amplitude that is coming from the first demodulator. And now at this point, we are driving roughly 2 volts or so that corresponds to the amplitude we are measuring. And also it is possible to scale it up. For instance, we were measuring around 200 millivolts, right, from the amplitude of the signal that we are measuring. Now it was already configured, so we were multiplying it by 10. So that's why the value is around 2. So let's don't scale it, for example. Let's do 1 here. Now the output is around 200 for exactly the value we have. And you can add up also offsets for your needs. You can also grab, for instance, the sweeper tool to sweep this offset to drive another instrument. So that's how you can do really, really complex control schemes and measurements using these devices.
That's a very nice answer. And there's also a quite related question. So if someone wants to feed an external signal, I mean, it can be a DC source meter, or let's say some arbitrary function generator to the instrument. Is it possible to read it?
Yes, so that's what I was doing actually in a bit. We have the scope, of course, and you can, with the UHF-LI, you can even measure it up to 128 megasamples per second as a two channels. And any signal you will get, of course, then you will measure. But one important aspect of it, for instance, if you are talking about arbitrary waveforms, it is important to have the triggers so we can align actually the scope shots with the incoming arbitrary waveform. And for that, we also have several trigger channels. In the front panel, we have 2, for example. Also, we have digital input-output channels that allows you to be able to first read other outside signals and also align the measurement with it using all the trigger and digital channels.
Indeed, that's also a very good answer, I believe. And I think this is also a bit related to that. You actually just now give a nice introduction to this PID and PLL, but I didn't see how it is possible to, for example, log it to an external frequency or external oscillator. Is it possible then?
Yes, indeed possible. So if I grab the lock-in tab again, now, so you see we have, we can configure the demodulators as manual, etc. And in this case, the first one, since we are using the PID so PLL for that is activated up here, down here, it says PLL. What we can do, we can configure this demodulator, for instance, as an external reference. This essentially configures a PLL as well. Now it does it. And then it will log to a signal. Now it doesn't do that because I didn't set it up properly. I probably could have done it. But in the end, what it does is it starts controlling the PLL here. And actually, you see that we have set up in the adaptive mode. And that means actually you don't need to adjust much. If you have a clean signal, in this case I don't have because the signal goes through the DUT, but maybe we can experiment a bit and do this. Okay, so this should work. So what I did so far is I am driving around 100 kilohertz, the signal input 2, and I am measuring it with this demodulator, and I switch to XREF mode, and then set it up to actually control the second oscillator. And you can see that the second oscillator is now oscillating around 100K, which means it's actually locked to the...
This is very nice, Kivanç. And I believe actually we are now reaching the end of this Q&A session and also the end of the webinar. So just to answer to the question of many audiences. So this video is recorded and therefore will also be sent to you in a following up email in the next couple of days. And in the email, we will also include the answers to the questions that we really don't have the time to address today. And a final but very important message to the audiences. Please stay tuned. We have a series of webinars coming in May. One is about photonics, another is about nanoscale transport, and more will come soon later. And thanks all for watching today, and we all look forward to virtually meeting with you again. Thanks.